In part 1, we built all of trigonometry out of a single circle. We learned that sine and cosine are nothing more than the shadow of a point going around and around. But that was just the beginning. Here is a question that circle cannot answer on its own. A ship is somewhere out at sea. From one lighthouse, you measure the angle to it. From a second lighthouse, a known distance away, you measure another angle. No right angles anywhere. No way to walk out with a ruler. And yet, from just those two angles and the distance between the towers, you can pin that ship down to the meter. Trigonometry can measure the things you can never reach. This is the advanced toolkit. We'll crack open the secret identities that let you bend any trig expression into a new shape. We'll solve triangles that have no right angle at all. We'll run trigonometry backwards. And then we'll uncover something almost unbelievable, that every single one of these rules is hiding inside one short, beautiful equation. Let's build the power tools. A 10-second recap. On a circle of radius 1, take any angle measured from the right. The horizontal position of the point is the cosine, the vertical position is the sine, and their ratio, sine over cosine, is the tangent, the steepness of the line out to that point. 3 functions, but there are 3 more, and they've been hiding in plain sight. Meet the reciprocals. Flip the cosine and you get the secant. Flip the sine and you get the cosecant. Flip the tangent and you get the cotangent. Secant, cosecant, cotangent. They're not new ideas, they're the same 3 functions turned upside down. But watch where they actually live on the circle because it's gorgeous. Draw the tangent line, the line that just touches the circle on its right edge. Now extend the radius outward until it strikes that line. The piece of tangent line you just created has length exactly equal to the tangent of the angle. That is why it's called the tangent. And the slanted line from the center out to that meeting point, its length is the secant, from the Latin for to cut, because it cuts across the circle. These names aren't arbitrary, they are literally what you see. Do the very same trick along the top of the circle, and the horizontal tangent line hands you the cotangent and the cosecant, the exact mirror image of the first 2. 6 functions, 1 circle. That is the complete family. Now the real machinery of advanced trigonometry, identities. An identity is an equation that is always true, for every angle, no exceptions. It's not something you solve. It's something you use, like a gear that transforms one expression into a completely different-looking one that means exactly the same thing. And they all grow from a single seed. The seed is this. On our unit circle, the point sits at horizontal position cosine, vertical position sine. But it's on a circle of radius 1, so by the Pythagorean theorem, horizontal squared plus vertical squared equals 1. In other words, sine squared plus cosine squared equals 1. This is the most important identity in all of trigonometry, and it is really just Pythagoras wearing a disguise. Divide that identity by cosine squared and a second one pops out. Tangent squared plus 1 equals secant squared. Divide instead by sine squared and you get 1 plus cotangent squared equals cosecant squared. 3 identities, 1 parent. From now on, whenever you get stuck, this little family is your escape hatch. But here's the question that unlocks everything. If I know the sine of angle A and the sine of angle B, what is the sine of a plus B? You might guess you just add them. You'd be wrong spectacularly. The sine of 90 degrees is 1. But the sine of 45 plus the sine of another 45 is not 2. It's about 1.4. Angles simply do not combine like that. So how do they? The answer is one of the most elegant pictures in mathematics. Stack 2 angles, angle A up from the floor and angle B on top of it. Now reach out along that top ray a distance of exactly 1 and mark the point P. We're going to find the height of P in 2 completely different ways and then force them to agree. Drop a perpendicular from P straight down onto the lower ray. Because the angle up there is B and our distance is 1, that little segment has length sine B, and the base along the ray has length cosine B, ordinary triangle stuff. Now the key move. The true height of P, above the real horizontal, is built from 2 pieces stacked on top of each other. The first piece, the base of length cosine B lies at angle A, so its own height is cosine B times sine A. The second piece, the tilted segment of length sine B contributes a vertical share of sine B times cosine A. Add the 2, and the total height of P is sine a cosine B plus cosine a sine B. But that height is also simply the sine of the whole angle A plus B. Set them equal, and there it is. Track the horizontal positions the same way, and the cosine of a plus B falls out too, cosine a cosine B minus sine a sine B. Notice that minus sign, it's where a lot of student algebra goes to die, so hold on to it. Flip the sign of b, and you get the difference formulas for free. 6 formulas, 1 picture. Now feed the machine its own output. What if a and b are the same angle? Then a plus b is just double the angle. The sine formula collapses to 2 sine cosine. The sine of twice an angle equals 2 times sine times cosine. And the cosine formula gives cosine of twice, the angle equals cosine squared minus sine squared. These double angle formulas are everywhere in physics and engineering. And because sine squared plus cosine squared is 1, that cosine formula can be rewritten to strip a square clean off. Cosine of twice, the angle equals 1 minus 2 sine squared. Rearrange it, and you can trade a stubborn sine squared for a plain cosine of a doubled angle. That one trick is how engineers tame the equations of alternating current and vibration. This is the whole point of identities. They aren't trivia to memorize, they're shapeshifters. A stubborn integral in calculus, a tangled wave in physics, a control system that won't stabilize, reach for the right identity, and a monster expression melts into something you can actually work with. Back to that ship at sea. Everything in part 1 quietly assumed a right angle somewhere in the triangle. But most triangles in the real world don't have one. A plot of land, a truss in a bridge, the path of a plane changing course. These are just 3 sides and 3 angles, with no 90-degree corner in sight. We need laws that work for any triangle. The first is the law of sines, and it's beautifully symmetric. In any triangle, each side divided by the sine of the angle across from it gives the same number every time. Side over sine A equals side B over sine B equals side C over sine C. Big angle, long side, small angle, short side. This law makes that relationship exact. Why is it true? Drop a single altitude, one vertical line from the top vertex down to the base. That line has a height you can write 2 different ways, as one side times the sine of an angle, or as another side times the sine of a different angle. Since it's the same height either way, those 2 products must be equal, and rearranged. That is the law of sines. One altitude, one line of algebra. This is exactly how you find the ship. 2 lighthouses, a known baseline, 2 measured angles, and the third angle is just whatever's left to reach 180 degrees. Now every side is reachable from that single baseline. Surveyors mapped entire countries this way, one triangle at a time, long before satellites existed. And astronomers used the very same idea to measure the distance to nearby stars, using the whole width of Earth's orbit as their baseline. But the law of sines has a blind spot. If you know 2 sides and the angle squeezed between them, with no matching angle and side to start from, it simply can't get going. For that, we need the heavyweight, the law of cosines. It says the square of one side equals the sum of the squares of the other 2, minus twice their product, times the cosine of the angle between them. Now look closely, because this is one of the great aha moments in all of mathematics. What if that angle is exactly 90 degrees? The cosine of 90 degrees is 0, so the entire last term vanishes, and you're left with c squared equals a squared plus b squared, the Pythagorean theorem. It was never a separate law. Pythagoras is just the law of cosines, for the one special case of a right angle. The most famous theorem in mathematics is a single frame of a much bigger movie. And when the angle isn't 90 degrees, that extra term is a correction. Open the angle wider than a right angle and the cosine turns negative, so the term adds length, the far side stretches. Close it tighter and the term subtracts, the far side shrinks. The law of cosines is just Pythagoras, with a built-in dial for the angle. With these 2 laws, no triangle is safe. Know all 3 sides, the law of cosines hands you the angles. Know 2 angles and a side, the law of sines finishes the rest. Every distance you cannot walk, every height you cannot climb, every angle you cannot reach becomes a number. So far we've only gone one way. Give me an angle, I'll give you a ratio. But real problems usually run in the opposite direction. You measure a ramp and find its rise over its run, now you want the angle. You need to undo the sine, undo the cosine, undo the tangent. Enter the inverse functions, arcsine, arccosine, and arctangent. Say a road climbs 3 meters for every 4 meters forward. The tangent of the slope angle is 3 over 4. Feed that to the arctangent, and it returns the angle, about 37 degrees. Arctangent is the function that answers, what angle has this steepness? Your phone uses it constantly, every single time it works out how you're tilting it. But there's a catch, and it's a deep one. Sine is a wave. It hits the value 1/2 not once, but over and over forever as the angle keeps turning. So which angle has sine 1/2 has infinitely many correct answers, and a function is only allowed to give one. So mathematicians made a deal. The inverse sine will only ever return an angle in a single chosen stretch, from -90 to +90 degrees. That's why your calculator gives you one clean answer, even though the honest answer is this, plus every full turn forever. This is the heart of solving trigonometric equations. When you solve something like sine of x equals 1/2, the calculator gives you the doorway, 30 degrees, but the full solution is a whole repeating family, 30 degrees, and its mirror at 150, and every one of those, plus a full 360-degree lap, again and again. In a world that spins, answers don't come one at a time. They come in endless echoes. Now for the moment everything has been building toward. All those identities, the angle sum formulas, the double angles, and rules we haven't even met yet, every single one of them is hiding inside one equation. And it connects trigonometry to a place you'd never expect, the imaginary numbers. It's called Euler's formula, and many mathematicians call it the most beautiful statement in the entire subject. Here it is. E, the natural growth number, 2.718 and so on, raised to the power I times theta, equals cosine theta plus I times sine theta. On the left, exponential growth but with an imaginary exponent. On the right are two circle functions. What it's saying is staggering, that growing in an imaginary direction is the very same thing as turning in a circle. Rotation and growth revealed as one act. Watch what this lets us do. Earlier, to get the sine and cosine of a plus b, we needed a whole geometric picture. Now use one fact you already know about exponents. To multiply powers, you add the exponents. So e to the I times a plus b equals e to the IA times e to the IB. Translate both sides through Euler's formula, multiply out the two brackets on the right, and then just match up the ordinary parts and the imaginary parts. And out they tumble, both angle sum formulas at once. The ordinary parts give cosine a cosine b minus sine a sine b, that's the cosine formula. The imaginary parts give sine a cosine b plus cosine a sine b, that's the sine formula. The picture we sweated over back in Act 2 just fell out of a single line of algebra. One formula, and the entire identity table writes itself. Push it further. If e to the I theta is cosine plus I sine, then raising it to a whole power n simply multiplies the angle by n. That's de Moivre's theorem, cosine theta plus I sine theta, all raised to the n, equals cosine of n theta plus I sine of n theta. Want a formula for the cosine of triple an angle? You don't memorize it, you expand a cube and read it straight off. Trigonometry has quietly become algebra. And run it in reverse, ask for the numbers that give one when raised to a power, and Euler's formula spaces the answers as perfect points around a circle. The solutions to a pure algebra problem turn out to be the corners of a regular polygon. Algebra and geometry, revealed as the same thing seen from two sides. That is the gift trigonometry gives to the rest of mathematics. One more secret. Our sine and cosine were born from a circle, the equation x squared plus y squared equals 1. But there's another famous curve that looks almost identical with just a single sign flipped. X squared minus y squared equals 1. A hyperbola. So here's the natural question. If a circle gave us sine and cosine, what does a hyperbola give us? It gives us their twins, the hyperbolic sine and hyperbolic cosine, spoken as sinh and cosh. These are built not from angles but directly from that growth number e. Hyperbolic cosine is e to the x plus e to the minus x all over 2. Hyperbolic sine is the same but with a minus. And they obey their own Pythagorean rule with a twist. Hyperbolic cosine squared minus hyperbolic sine squared equals 1. The same shape as the circle's identity, but with a minus, matching the hyperbola perfectly. And these aren't distant cousins. They're the very same family. Euler's formula quietly tells us that if you turn through an imaginary angle, the circular functions become the hyperbolic ones. The circle and the hyperbola, sine and hyperbolic sine, are two faces of one deeper object. The wall between them was only ever the imaginary line. So where do they actually show up? Hang a chain, or a power line, loosely between two poles, and the curve it settles into is not a parabola as everyone assumes. It's a hyperbolic cosine, the shape we call a catenary. Flip that curve upside down and you get the strongest possible arch. And in Einstein's relativity, motion near the speed of light is described not by circular rotation, but by hyperbolic rotation. The twin functions run the universe at its extremes. Here's a question that sounds simple but really isn't. When you type the sine of 1 radian into a calculator, there is no triangle inside that chip. No little circle spinning around. So how on earth does it get the answer? The surprising truth. It adds up a never-ending sum of simple powers. This is the secret formula. The sine of x equals x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040 and on forever. Each term is smaller than the last, the signs keep flipping, and the denominators explode. Add just a handful of terms, and you already match the true sign to more decimal places than you will ever need. A smooth, curved wave built out of nothing but straight powers of x. And here is the thread that ties this entire video into one knot. Write out that same endless sum for e to the x, then feed it the imaginary angle from Euler's formula. The terms split into two streams. The even ones line up perfectly into the series for cosine. The odd ones line up into the series for sine. Euler's formula was never a lucky coincidence. It's exactly what you get when you look at these infinite sums the right way. The circle, the identities, the twins, the machine, all of it, is one single idea, viewed from different sides. Look how far a single circle just took us. It started as the shadow of a spinning point. From that, we unpack the identities that reshape any expression, the two laws that conquer every triangle, the inverse functions that run it all backwards, one magic equation that binds trigonometry to the imaginary numbers, a hidden twin born from a hyperbola, and an infinite sum that lets a machine draw a wave. Because trigonometry was never really about triangles. It is the mathematics of anything that turns, anything that repeats, anything that waves from the tides to the alternating current humming in your walls, from radio signals to the orbits of the planets. It is the grammar of rotation itself. And you now speak it fluently. If this made the pieces finally click into place, that's the whole reason it exists. Trigonometry, from the circle to the cosmos. See you in the next one.